Yes.
All right, so let's just get started. First off, this is just a basic outline of all of the things that we're going to be going over with this presentation. So first, I'm going to start off with an overall contributions that this paper presents. And then I'll also go through a quick run through of the Price of Anarchy, the definition of it, as well as the general way that we prove an upper bound for the Price of Anarchy. Once we go through the overview, we're going to be hitting the main contributions that this paper presents. And then doing a review of it, and then any open questions that this paper proposes. Okay, so an overview of the contributions for the paper. There are three main contributions that this paper presents. This first one is identifying a canonical proof template. This proof template is used in order to derive the upper bound of the Price of Anarchy for pure Nash equilibrium. The second contribution is showing that the bound that we found in this first contribution with the canonical proof template is going to extend to the rest of these equilibria shown in this diagram. There's four of them. PNE stands for pure Nash equilibrium. MNE stands for mixed Nash equilibrium. Core EQ stands for correlated equilibrium. And finally, CCE stands for coarse correlated equilibrium. And again, just the bound found with the canonical proof template is going to extend to all of these classes or equilibria. And then finally, identifying a class of games. And we're going to be most notably going over the congestion games, where this upper bound of the canonical proof template is going to be tight across all of the equilibria. So again, basic definition of Price of Anarchy. It's this following ratio over here, the performance of the worst case Nash equilibrium, divided by the optimal performance if the agents are not to decide on their own. I would also just like to note that you want to have this Price of Anarchy, this ratio be as close to 1 as possible for the most optimal results. And then how to prove the upper bound of Price of Anarchy. The general way that we had done it in class and how it had been done for a while is just first we assume that the pure Nash equilibrium, or assume we have a pure Nash equilibrium S and some optimal deviation from that S star. We want to prove that for each player of I, that this inequality over here shows, and the left-hand side is the cost for player I if they were to play strategy S, and we want to show that's less than or equal to the cost to player I if they were to deviate to strategy S star, and all other players remain the same. And so all you have to do is sum both sides of the inequality for all agents, assume there are K agents, to get this following inequality over here. I'd also like to note that this right-hand side of the inequality is the cost is this entanglement of these two strategies, S and S star, and it's going to lead into the third step, which is generally speaking the most difficult step, relating the inequality to the pure Nash equilibrium strategy S and the optimal deviation S star in order to get this specific inequality. This specific inequality is specifically for congestion games. And notice that the right-hand side of the inequality becomes this disentanglement of S star and S. This is the hardest part, but once you get to this third step, then the fourth step is pretty easy. You just solve for S, and for, again, congestion games, you get this upper bound on the Price of Anarchy, which is 5/2. Yeah?
Just a small question. Optimal deviation S star, is that deviating from the optimum, or that is detailed more?
Oh, okay. So when it says this optimal deviation, that's just like a deviation from the pure Nash equilibrium.
That should be 5/3, right?
Oh yeah, sorry. That's a typo. That should be 5/3. My bad. Yes. So okay. Now we can get into the actual contributions of this paper. This is the first one, and it's this idea of smooth argument, or the idea of the smooth argument is the canonical proof template that I had said before. Also, when we're talking about games, for now, we're going to be assuming cost minimization games. This also works for cost maximization games, but trivially. So a game is considered to be lambda mu smooth if for every pair of outcomes, S and S star, that you have that following inequality over there. Note that the left side of this inequality is the exact same as the right side of the inequality on this slide on step 2. And then you want to show that this is going to be less than or equal to lambda times the cost of strategy S star, or outcome S star, plus mu times the cost of S. if we show that, or if we get some lambda that's going to be greater than 0 and some mu that's going to be less than 1, then we can show that the upper bound of the price of anarchy is going to be lambda divided by 1 minus mu.
Okay, so it might not be super obvious, I guess, how exactly you get this price of anarchy upper bound, and I'll show that in a second, but I just want to mention something really quickly. Right, so where we get this definition from is we're basically sort of, we're taking kind of the hard part of these price of anarchy proofs and we're encoding it in this definition. So that's just sort of a little intuition, right? We're saying that for any two outcomes, we can sort of charge back or unentangle the cost of those two outcomes, right, by some sort of scaling factors. Okay, so let's go ahead and prove how you get this price of upper bound on the price of anarchy. So there's not a lot we've assumed about this game, so the proof is pretty simple. We just kind of, I don't know, just work through it and it kind of just proves itself. So we'll start off with a little bit of notation. We have S, which is some sort of Nash equilibrium, and S star, which is sort of the optimal. Again, this is cost minimization, so we have an objective function we're minimizing. Assume that the game is lambda mu smooth. That's assumed. Right, so here's our objective function. We're trying to minimize the cost, and we'll say the cost is the cost incurred by the players summed. Right, just quick definition. Okay, so then our first kind of step is that we made this assumption that we're at some sort of Nash equilibrium, and deviating from that Nash equilibrium, obviously by definition of a Nash equilibrium, is going to incur more costs. Right, otherwise it wouldn't be a Nash equilibrium. So we get this sort of inequality here, and then you'll notice that this right here is exactly the same term that we had for our definition of smooth games. So we can go ahead and put this upper bound here, which is the lambda cost, mu cost, right? So from this, you just sort of rearrange the terms. In case it's not obvious, you subtract the cost times mu and then divide through, and you will get that there's an upper bound of the price of anarchy, and that's lambda over 1 minus mu. Any questions on how we got there? No? Okay, cool. So here's the sort of the definition. I have both the minimization version, the maximization version. Also, I guess I should note, maybe for the maximization version, that we don't need mu to be less than 1, right? Because we can still get a price of anarchy bound on that. Okay, so that's kind of cool. But we get a little more with this definition, right? So we've said before that this is like a robust price of anarchy. What exactly do we mean by that, right? And what is that more that we get? What is that robustness? So if you look back at our definition of smoothness, you'll notice this definition is a little bit more stringent than we really needed to prove that other proof, or to prove this price of anarchy. And how is it more stringent? Well, we're saying that for any two outcomes, S and S star, you can do this unentangling, right? If you look back at the other proof, right, we're starting from a Nash equilibrium, right? So that's fine, but it's not really, we don't need that, right, to use this definition. Right, and so because of that, because this definition is so much stronger, we're able to look at sort of looser definitions of equilibrium. Specifically, the loosest definition is coarse correlated equilibrium, right? So we reviewed coarse correlated equilibrium in class, but just in case someone forgot, it's just some distribution sigma, where changing out of that distribution, you're going to be worse off. And because it's a distribution, it's randomized, so we're talking about expected outcomes here, but same thing. Also, I want to point this out because I think it kind of gives a little bit more meaning to this, right? So it's known that computing pure Nash equilibrium is computationally intractable. It's something that we can't do. But coarse correlated equilibrium is something that we can do computationally efficiently, right? And so because of this sort of robustness in the price of anarchy, right? So generally we kind of make the assumption, well, if it's computationally intractable, then agents probably aren't going to, move to that equilibrium. Right, but because coarse correlated equilibrium is tractable, right, we can say that, well, this sort of price of anarchy upper bound still holds in kind of when we're sort of taking into account where agents are actually going to end up, right? So that's kind of a sort of cool sort of I guess sort of result, right? Okay, so let's go ahead and sort of prove that this is also an upper bound. So again, we have our what it means for coarse correlated. Right, so we'll start off with our objective function. Again, that's cost, some of the costs incurred. I guess this could also be equals, but it holds either way. So then first step, and again, these proofs are pretty simple because we haven't really assumed a lot about these games. Once you have this condition, right, this sufficient condition shown, the proof kind of writes itself, and you'll see that. So from our objective function using linearity of expectations, we go ahead and throw the expected inside the summation. Pretty standard stuff. Then from there, we're going to go ahead and assume that we're changing, right? So this is the definition of course correlated equilibrium, right? And so this, I guess there's a sort of this is greater than this, right? So this inequality still holds, right? So, we're changing now, we're, to this other deviation, and we're going to be worse off. So then we again use linearity of expectations, right? So we go ahead and throw the summation back in, and then you'll recognize, oh, look, that's this same term that we've touched on again. It's that smooth game sufficient condition. So go ahead and sort of substitute in what we, again, another upper bound, right? So we're staying with upper bounds, right? From what we've shown, right? I guess we're assuming sort of that it's smooth. And then from here, just sort of use linearity of expectations again, and we throw this expected here on S. And the reason we can do this, if it's not obvious, is that S star is the optimal, right? So that's not randomized. We're only pulling from the deviation for S. So this doesn't need to be expected. And then from this looks pretty familiar. It's basically the same with the pure Nash equilibrium version, right? And so we just sort of subtract the two, divide through, boom, we have again a price of anarchy upper bound, which is at worst lambda over 1 minus mu. So pretty cool stuff. But so what, right? We have this definition, and sure, this definition, it proves some stuff, but to be honest, definitions are a dime a dozen. Anyone can come with a definition that does some shit, stuff. But is it useful, right? So it turns out it is useful. So if you look in the literature, there's a number of Price of Anarchy proofs, specifically in Tim's work. It's like he basically makes a smoothness argument. But in other ones, you might have to do a little work, but if you look at it, they basically do all the hard work for you of showing that you can disentangle these two outcomes, right? So it turns out that, when we were, this is, a couple of years ago, but, when just sort of moving, trying to find this Price of Anarchy upper bound from pure Nash equilibrium, using this sort of smoothness argument, we can show that actually it's a Price of Anarchy upper bound for course correlated. So it is in fact useful. But then there's another question, and if you're a skeptic like me, you'd probably be thinking, well, okay, this definition seems pretty useful, right? But it seems maybe it's a little bit too general, right? I guess sort of the natural question is, are we losing anything when we use this definition, right? Is the Price of Anarchy upper bound that we're showing maybe not as optimal as we'd like it to be? And so for certain interesting classes of games, the answer turns out to be no, specifically congestion games.
So I have a couple of questions.
Yeah.
Right, so you showed it for pure Nash,
and
you showed it for course correlated.
Correct.
What about in between?
Yeah, it holds for all of those.
Okay.
Yeah.
Because they are sandwiches, right?
Exactly. But so in the paper, he does show specific arguments for those, but because all of those are encompassed by course correlated, just to, so we have limited time, no point. Yeah.
And another question that is not very important, but just for curiosity, the Epstein guy, is it our Epstein?
No, I think it's our Epstein has two P's.
Two P's, right?
Yeah, I think this is a guy.
Okay.
I think they're from like Tel Aviv, I think is where they are, but I'm not 100% positive on that. But yeah.
Yeah, awesome. So we spoke, hey, congestion games, it actually does show a tight bound. So this is actually useful. And to explain that, I'm going to be slightly dissecting this little definition of what we mean by tightness. So if you look at this side, you have exactly what we showed by smoothness. We've shown legal values of lambda and mu, and we get this POA. That's lambda divided by 1 minus mu. In A means that it's just legal values, so the smoothness condition holds. And technically, you can have infinitely many such values of lambda and mu. You can set them both equal to the big values, but we want to kind of minimize the lambda divided by 1 minus mu, find values of lambda and mu that minimize this. On the left-hand side, this is just a POA of a game G within some set of games. So as we kind of talked about, we'll be speaking specifically about congestion games, and also within congestion games, it's games with fixed cost functions. So if you have a fixed cost function, in class, we looked at a few affine functions. So we looked at C of X equals to 1. So each edge has a fixed cost. We looked C of X equals to X. We also looked at some maybe polynomial functions, but as long as you have a fixed set of cost functions, this will apply. And so how do you actually, key point is that with the inequality, if you say that a less than equal to sign, that we know with all smooth games, this is a bound. The question is tightness just means you change that inequality into an equality. And by the way, cut me off at any time, please. So how will I be kind of showing this with congestion games? I actually won't. This gets to be quite technical, and it's many pages of just technical equations, but I'll be giving you a key idea of each side. So I'll be giving you a key idea of how you minimize this side, so find values of lambda and mu that minimize this, and how you come up with a game G that has an equivalent POA to lambda divided by 1 minus mu. And obviously, if a game G exists with an equivalent POA, and we know a less than equal an inequality, we can use that to show a tightness inequality bound. So beginning with how do you minimize lambda and mu, this is the exact same definition we showed you a few slides ago. You can kind of fix these S values. And if you fix these S values, you'll see that the only two things that change in this equation is lambda and mu. So on the left-hand side, this is going to be fixed, but both costs will be fixed. And you just get an inequality with changing values of lambda and mu, which is exactly the definition of a half plane. So you have a half plane of legal values of lambda and mu that fit this inequality. And you can come up, and I'm not going to go into specifics on how you do this, you can come up with infinite possible half planes of sets of values of lambda and mu such that they fit this definition of smoothness. Now, what do? You want to pick values of lambda and mu that minimize lambda divided by 1 minus mu. And this function looks a little bit funky, but a key thing that you should notice is that you always want lambda to be as small as possible, and you always want mu to be as small as possible. That by itself isn't enough, but it gives you a kind of intuition on when you will see, and on the next slide, I'll show you visually, these sets of half planes, you kind of intuitively want to go bottom left, bottom going down in lambda and left going down in mu. And using this, you can find minimum values, and one of them will also minimize lambda divided by 1 minus mu. And again, if this doesn't make complete sense, I'll be showing a bit of this on the next slide to help you build an intuition. A key point is that you only have two things changing, which is awesome. This means that these half planes will be two-dimensional, which is the easiest case of half planes, and it's easy to visualize. And let me actually show you an example on the next slide. I'm going to be using a congestion game, specifically a congestion game that we looked at in class, in which the cost of each edge C of x is equal to x, as they say below. And I'll be using the simplest example in which you only have two people playing. And this can apply to infinitely many people playing. You actually can come up, I think, with six distinct equations, six equations, but out of them, you only get two distinct equations of half planes. Now, this doesn't look like a half plane because they only showed the line, but the half plane actually extends infinitely up this way. Again, because lambda is limited at 1, because lambda can't exceed 1, because then this becomes all funky. But anything in this section is actually legal values of lambda and mu that satisfy the smoothness conditions. But since you want to minimize lambda and mu, I'm only showing the edges of these half planes. And intuitively, the minimum value is going to happen at the collision of at least two half planes. In this example, it's convenient you only have two half planes, but technically you can have infinitely many of them, and you just kind of want to go down bottom to the left, look at those kind of collision points, and that's going to tell you what you need. So again, the steps that you have to do is plot the half planes, find this minimizing collision point. In this case, it happens at these sets of values. These values should look like something that you know, because again, you can plug these values into the POA equation, and you get exactly 5 divided by 2, which is what we showed you is the POA of congestion games, and what we showed you a few slides ago, and we looked at this in class. And again, this only uses two individuals, and this is the n equal to 2 case. Now, this again is just using smoothness, and it doesn't tell you anything about the tightness of this bound. We know this tight to be bound to be tight, but this doesn't show it. So you actually have to go to the second side and see, can we come up with a game that actually has a bound that's just this tight? Does anyone have a question? No. Okay. This, I'll admittedly, I'll be kind of hand wavy because we just don't have time. This is like a few pages of just deep technical details, but I'll be kind of giving you a sense of intuition, and that is you'll always get a collision between two half planes that minimizes lambda divided by 1 minus mu. And you use each one of these half planes to define, and each one of them uniquely defines a cycle that you can make between these nodes. And one of them you use to make a kind of small cycle going one way, and this isn't complete. And one of them is a long cycle, which involves visiting many nodes. And these cycles will be completely independent. And each individual has an option between going on the long cycle and going on the smaller cycle. Now, this is skipping some of the details. Actually, they'll have to do a combination of both cycles in both cases. but I'm just simplifying it as much as possible, just with the intent of giving you a sense of intuition. Optimally, they'll all use the smallest cycle. This is the optimal solution, but based off of these half planes, and because we use these half planes to define it, we show that the long way, if they all go the long way, it is also notch. And it's notch in the sense that if any of them deviate, they actually can get a solution that has an equal cost, but they actually can't beat the cost. So it's exactly at that equality, and because that's at the bounding line of one of these half planes, it is notch, and it's exactly on the cost. And this is just a little bit of intuition. Even though I said we only have n people playing, you might be asking, why do we have n+1? Don't think about it too much. If you have questions at the end, I'd be happy to help. But in the smaller solution, each one of them visits exactly one edge. And so each edge has a cost of 1. So the total cost is n+1 times the cost of 1. In the long solution, they'll be visiting all the edges but 1. So they'll be visiting n edges. So this n is how many edges they visit. Each edge is visited n times. So you have cost of n, and you have this long cost. And actually, they can't deviate out of this. And it's exactly, they can't deviate out of it. And you can see by dividing these two values, you get a POA that is at least, because we found an example of a POA with the C of n times n divided by C of 1. And this should not be obvious to you, but you can take this maybe on faith at the moment that this is the exact bound that is equal to the bound that we found in the last example. And this actually shows an example of a game that has an equivalent bound, which means that that bound must be tight. Does anyone have questions? Because this is a bit, my explanation was a bit hand-wavy. Okay, well, maybe at the end you'll have some questions, but I'll leave you with that.
All right, so just a quick overview again on all three contributions that this paper has presented. The first one, the canonical proof template, that's this idea of the smoothness argument that we've been going throughout this entire presentation. And then the second contribution that Freddie had gone over, that was this idea of proving that that the canonical template is going to extend to the coarse correlated equilibrium, and that's what he had proven. And then you can just assume that since it's for pure Nash equilibrium and coarse correlated equilibrium, that it's sandwiched between these two. That was also the exchange that Giannis and Freddie had very briefly. And then what OPEC had just went over, the third contribution, is showing that for a class of games, specifically congestion games, that the upper bound found with the canonical proof template is going to be tight, using the half planes argument in order to minimize the upper bound cost of the Price of Anarchy with the canonical template, and then the cycle proof in order to show the worst case Price of Anarchy for congestion games. And then, so we're ending with just some open questions that this paper presented. So the first one, are there any other classes of games such that the proof of the canonical proof template is going to be tight for, as well as are there any classes of games such that this isn't tight for, if there are any at all? And then also, does it hold for collusion? Because with the Price of Anarchy, we had assumed that it's the worst case scenario for Nash equilibrium if no one's cooperating, but does the smoothness argument